Well, welcome again to Firing of Ceramics, an American Ceramic Society and Dennis Brosnan collaboration to provide a self-paced educational course on the Zoom platform. Today we're talking about firing alumina. And many of you know that alumina is really a backbone of ceramic products. Pure aluminum oxide came into good supply after World War II, so many alumina products have been developed, and especially in recent years, for use in ceramic compositions. Today we're talking about those compositions that typically are in the 90 to 99% alumina range, and I'm going to focus my comment on refractories, which are usually comprised of alumina gradations from coarse materials, perhaps 2 to 4 millimeters in particle diameter, down to very fine particles that are in the micron size area. These ceramics are typically graded in sizing to achieve the maximum density and pressing, and then they're fired to meet the product standards that there are for these types of products. Now, today we're going to talk about two products, and we'll talk about compositions around 95 or 96% aluminum oxide and lower. And those are products where a glass phase is involved. And of course, alumina or corundum is the major mineral that's present. But as you can guess from the phase diagram, mullite is also present. We're also going to talk about products up to 99% alumina. And so the sintering strategies are a little bit different there. And so we have examples of both. Now I understand that many people make fine aluminas that don't contain such coarse particles. And there are all types of products out there made of very fine alumina at very high purities. So I have to talk about things that I have experience with. And so we're going to focus this on how do you fire these types of ceramics. Now, one of the differences between the past classes is that we're considering systems where crystal to crystal bonding predominates. Corundum, alumina crystals, corundum crystals to corundum crystals bond directly to each other in the systems we're talking about. The higher the percentage of alumina, of course, the more this comes into play. Melted phase can play a role in achieving some of that bonding, particularly when you're below about 97% alumina or thereabouts. When you're above that 97%, if you get to the 99%, melting phase is a secondary phase, not quite as important. However, we may use some techniques to create a slight amount of melted phase to help us in sintering. Typically, the products that I talk about today are going to have about 18% porosity or less. Typically, 16% is very common for those. The pore size distribution becomes very important in improving thermal shock resistance or providing thermal shock resistance in these products. Another way of saying this, it improves the fracture toughness. Corrosion resistance, of course, is very important in a number of these products. Corrosion against liquid slags and things of this particular nature. So we'll review just a bit, 3 or 4 slides that we've talked about last time. Of course, we've talked about vitrification, and that's when we have particles and they form glass near points of contact, and we get these little center necks developing right at the points of contact. The driving force is to reduce the surface energy, and the glass migrates to these points eventually. The glass can be of a transient chemical nature and always approaches the final composition given on the phase diagram, but rarely ever gets there. Now, in reactive sintering, we also have a glass phase that forms between particle contacts, and then that glass phase further reacts with other substances there, maybe the major aggregates, to create a second crystalline phase. Glass phase may be there. Glass phase may be transient in nature, meaning it can go away after the product has reached its maturity. But nevertheless, we're going to have a reactive centering situation with a major mineral, in this case being corundum, and a minor mineral, in this case being mullite, and perhaps a little bit of glass that's present. Last time we talked about porcelain products, and these were really highly vitrified ceramics containing up to about 30% glass or thereabouts. The triaxial porcelains were made of crystals or granules of quartz, typically minus 200 mesh ground silica called potter's flint. Clay, typically kaolin, which served the function to provide a binder in the shaped product and also provide mullite. And then there's feldspar, which is a major component to forming that large amount of vitreous phase. Recall that when we talked about earthenware ceramics, the amount of vitreous phase was maybe as high as 6% or thereabouts. But now we have a very large amount of vitreous phase, and we see residual silica particles in this microstructure. We see a continuum of glass with little black pores in it. And this may be a clay relic showing mullite crystal development on the surface. So that was hard porcelain. There are many types of porcelain, and we didn't certainly try to cover them all. One important slide was the sequence of events on heating. At about 1,000 degrees, we begin to get some melting, and a little bit above that temperature, we can begin to see some shrinkage in the product in firing. 1,100 degrees C, we have the formation of a feldspathic glass. In some products, you may have a ramp in the heating schedule, firing schedule up to about 1,100. You may slow down at 1,100 and heat more slowly to try to enhance the development of this glass phase. A little bit higher, we can begin to develop not only mullite on the relics of clay crystals, but mullite growing out from the clay crystals. Eventually, about 1250 degrees C, we can begin forming secondary mullite. That's mullite crystals that grow to very long sizes, long fiber sizes. Their aspect ratio changes, and these crystals really impart viscosity to the glass phase. Now, some of the alumina from the metakaolin is dissolving in the glass. I realize that. So various things are happening to increase the viscosity of the glass phase, and that's good in enabling us to maintain our shape in our object that we are firing, because we get up to some temperatures that are pretty high here, and we can form a glass. We don't want the product to deform. Also, last time I showed you some photomicrographs of a body where primary mullite had formed on the kaolin crystals. Eventually, the feldspathic glass attacks those clay relics, and we get mullite needles developing more readily around the rim of the clay relics. And eventually, then we get a lot of crystals out into the pockets of glass, really providing what some people would say a binder in this situation. You'll recall that last time I also talked a bit about the conversion process for quartz. In this situation, I showed you the feldspathic glass and the mullite in this little diagram with a relic of what originally was potter's flint or quartz crystals. The conversion of quartz, beta quartz to cristobalite occurs along with the attack of the feldspathic liquid on the grain boundaries in this polycrystalline quartz. they open up, that releases a little bit of the compressive stress that's developed within the particle, and the cristobalite readily forms. Then we get very little tritomite in this situation. I have seen it before in very coarse grain silica bodies made out of Ganister silica rock. But in pottery, I don't think that we normally see that much. Of course, the inversion of quartz on cooling. Here we're cooling a body that contains both beta quartz. So in cooling, it inverts back to alpha, and we get a little bit of a 2% volume decrease right at 573 degrees C. And because of that, okay, I'll move that back. Because of that, we have to cool more slowly through the quartz area. So that's another reason that ceramics can be, firing schedules can be adjusted to be very slow cooling through quartz, because that quartz inversion can cause cracking. And if cracks link up, then your product can fracture more readily, either in the kiln or later on. So if you want to meet your strength standards, you're probably going to cool in a controlled manner through the quartz inversion. Now, if we did form some cristobalite, or if we only have cristobalite there, then we're also going to go through a beta cristobalite to alpha cristobalite inversion on cooling at 8.7 volume percent decrease. And you can see that's a little bit more decrease right there on this dilatometer curve. And here we have to be very aware of this, because cristobalite inversion is primarily blamed in technical literature for dunting or cracking of ceramic ware and cooling in kilns. Of course, I also talked about delayed dunting in porcelain products, which can happen minutes or hours or days or years later from when the product was made. In other words, this dunting process can impart stress within the ceramic, and eventually cracks can link up and cause failures. And so sometimes toilets will fail, but not very often. I mean, this is a very small amount of time by delayed dunting, and it can make the products weaker. Well, enough about review. So today we're going to talk about firing alumina. And of course, I've shown the alumina silica binary phase diagram again. So you know that when you get up here in the 90 to 100% alumina, you expect corundum and mullite to be the equilibrium phases in the product. We, of course, would expect pores and cracks, and we'll find that we can have a little bit of liquid residual in these products on firing. So the melting point of alumina is way up here at 2050. And so if we would say that centering temperature should be about 90% of the melting point, well, that's going to give us 1845 degrees C as the firing temperature for pure alumina, and that's impractical. It's just not going to happen in high production ceramic factories. So therefore, we have to engineer our products to get firing temperatures down to something practical, like 1750 degrees C, which can be achieved in a gas-fired furnace. Now, historically, because of these melting relationships and furnace capabilities, we added silica to make what you might call alumina porcelains. And that was because the raw materials that we had, and in terms of coarse alumina sources, which we'll call tabular alumina, fine alumina sources, which we'll call calcined alumina, and other additives that go into the mixture, we could make products at 1750 with a little bit of liquid phase. Now, of course, today we have more reactive aluminas, different calcines and different particle size distributions. So we're able to make 99% alumina structural ceramics in fine particle gradations that meet density and strength requirements. Now, just as a little background, if you want to make something that contains alumina, well, you're going to start out with kaolin at about 40%, but if you want to make more alumina content in the fired product than that, then you're going to go to something else. Like number 2 is andalusite. That's a natural mineral that's imported into the United States. And naturally it's 60% alumina. But if you want more alumina than that, you might go to a bauxitic kaolin, which can get you up to about 70% alumina or thereabouts. That's the raw material available. If you want more alumina than that, you're going to go over here to bauxite, calcined bauxite, which occurs in many areas of the world. It has aluminum oxide or corundum crystals as its main ingredient, but typically calcined bauxite is going to be about 88% aluminum oxide. So there's 12% of something else there, a lot of silica and some iron and titanium, things of this nature. During World War II or thereabouts, the Bayer process for refining alumina was present. So very high purity aluminum oxide became available. And so that's the Bayer process aluminas that I've given here. Now, we're going to talk today about tabular aluminas. Tabular aluminas are so named because the crystals of corundum, the individual crystals, are tablet shaped in nature. These are really high fired products. So they're very stable aggregates at elevated temperature, meaning they don't shrink much when you heat them to a very high temperature after you've made your product. We're also going to talk about calcined aluminas, not much about reactive aluminas, but calcined aluminas are fired at lower temperatures, low enough temperatures only to form aluminum oxide, but to leave them more reactive so that they will sinter more readily. And so these compositions are generally about 98% plus aluminum oxide, a little bit of silica. They're also characterized by their soda content, their sodium oxide content. If you don't know about the Bayer process, you can look up Wikipedia, which I give full credit to, and of course, the Bayer process is a caustic digestion of aluminum oxide. Caustic soda is added, sodium carbonate, or sodium oxide, rather, sodium hydroxide. I'll get this right. Then that's going to remove some of the aluminum oxide into a liquid phase, leaving a red mud residue because of the iron. Then we can crystallize out the aluminum oxide as aluminum trihydrate. And we can take that trihydrate, briquette it, run it through a rotary kiln. And if it's super high calcined, we'll make tabular alumina. If it's lower temperature calcined, it'll be calcined alumina as our raw materials. Now, tabular alumina is sold by Almatis in the grades T60, T64. I'm not biasing my comments to the company Almatis, but to my knowledge, they're the global leader in producing aluminum oxide. And here in their data sheet, they say that's calcined to 1800 degrees C. That's a pretty high temperature, and typically in a rotary kiln, so sometimes it's challenging to measure temperature there, but nevertheless, it's super high calcined. Calcination temperatures renders it what the old guys would call dead burnt. It doesn't change very much. It's not very reactive, but certainly in refractories that can be useful for strength, slag corrosion, and high temperature load bearing capability. One of their data sheets from Almatis shows you some information about some of the tabular alumina. All the sizes are 99.5% aluminum oxide. So if you want to make something that's 99% aluminum oxide, you're going to start with grades like this. There are some other sizes available to you. You can see that soda and silica and some magnetic iron is given. The aggregate is porous. It has a little less than 5% porosity. If you polish this and look at it on a microscope, you will see some pores within the corundum crystals. So that's kind of what you expect with tabular alumina. It's available in different particle sizes from the supplier, or you can buy it as aggregate and crush it yourself. But nevertheless, you can see it's available here in the coarsest size 3 to 6 millimeter, and then in some finer coarse sizes, mediums, and finer sizes here. So the screen sizes, screen fractions are available, or you can buy it unscreened. Now, Amalgamatus, as you would expect, also makes fine aluminas, which are the calcined aluminas. You can buy these in various grinds. So sometimes, even in fine sizes, they are agglomerated. That becomes important in some products, especially those that are made containing water, like refractory castables. Or it can be super ground into more or less individual crystals. Of course, once again, we have some of the grades of aluminum oxide. A2 is one that I'm very familiar with. It's an older grade of alumina that's still used out there in a lot of products, and you can see some of its properties. For A2, there's a little bit of residue left on a 325 mesh screen. Their surface areas are a little less than 1, so they're finer products, but not super fine. Other products can become finer. We're going to give an example today of a product made with this CT800. And so you can look and see that it has a surface area that's up there close on the average to around 1 or thereabouts. Well, that's some of our raw materials, but not all, because typically we will have to add binders to these products. They're made by various pressing processes, either dry pressing or isostatic pressing, whatever the case may be. But typically in the products that contain a little less than 96% alumina, we might use clay as a binder in pressing. If we're up at 99% alumina, we probably will use organic binders, and these could be carboxymethyl cellulose or things of this nature, that polyvinyl alcohol, whatever might be used in binding. There can be a small percent of glass forming products used in these products. Well, I guess microsilica is one that's used in a lot of products. We were putting microsilica into refractory bricks way back in, the 1970s. So that's one. Another one that might be presently used is lithium silicates, used in aluminas. And very fine lithium silicates with good mixing can be dispersed in small quantities. We're talking about quantities less than 1/10 of 1 weight percent. If you are using organic binders, then of course, I was taught as a ceramic engineer that binders burn out, carbon oxidizes. Well, that's not always the case with some of these higher molecular weight substances that are used today. You can see that wax will evaporate at fairly low temperatures. Polyvinyl alcohol goes through a loss of some water and depolymerizes. breaks into molecular fragments and evaporates above about 400 degrees C. So you can see the same kind of information from cellulosics and polyethylene glycol used as a lubricant, and a lot of our products will depolymerize around 180 degrees C. Of course, it's always important to get these binders out before any sintering begins. So that leads to firing strategy number one. Make sure all the binder is removed in heating before the onset of liquid formation or before the onset of sintering. Carbon, if it's persistent, will interfere with the sintering process and oxides. And so you don't want it there. With glass, it will interfere with the wetting relationships of the glass on the aggregate. So you want to get it out. So in evaporation of binders, you might want to give, of course, in preheating enough time for this evaporation to take place before you begin elevating the temperature rapidly toward any sintering temperature. Now, I'll talk about a little bit of information before firing. Your other courses that you've taken in ceramic technology talk about maximum density. And so we as ceramic engineers were told to mix coarse and medium and fine particles together until we get a maximum density. And so on this triaxial diagram of different particle sizes, we would find maximum press density in some particular area. And that's what we typically want. But particle packing is not it entirely, because there are other steps that contribute to the development of the fired matrix. Now, when I use the word matrix, I'm talking about the fine particles surrounding the coarses and mediums in the microstructure. That's what the product is like. We have a skeleton of coarse particles surrounded by mediums and fine particles, and we've done everything to get the maximum density we want. But remember that our goal is to form direct bonds. Now you engineer the product to have a continuous matrix. You want the coarse particles to be surrounded by matrix particles so that we can achieve fine binding. Of course, you want to use the least water content that you can in making these products, because water takes up space in the formed composition. So this is a picture of the intensive mixer in my laboratory. You can see that there's a rotating pan where the material is charged into, and there is a high-speed agitator that is inserted into the material that lifts the material and knocks it around and helps distribute that liquid. So this is an intensive mixer. If you have such a mixer like this, you can do wonderful things with a microstructure. If you have an inefficient mixer, you probably can't. So the future direction, I think, in aluminum ceramics is going to be to engineer the matrix in the fired product. Why is that? It's already happened with castable refractories. So nevertheless, these mixers let you engineer the matrix, put in very small additions to aid in sintering, to act as mineralizers, whatever the case may be. Forming is usually done in these materials by dry pressing. Of course, what happens in dry pressing is you can entrap air in the body. And if air is entrapped in the body, when you eject the part from the die in pressing, it can tend to grow a little bit. That's called springback. Okay, increase in volume a little bit. So there are a lot of strategies to try to prevent entrapped air. One is to have a more permeable matrix phase so that air can get out. Another is to use impact presses or friction presses, which we'll do a pre-compaction step. You can do that, of course, on a hydraulic press. Pre-compact it at low pressure, give it a dwell, let the air get out, and then press it to final density. So you'll see an example of using friction presses later on in this presentation. They basically use momentum to provide energy impact of the material. Typically, these are called bumps. And so by giving sequential bumps, we can de-air the material. In the most extreme case, people have put vacuum bells down over the press where the material is and sucked a lot of the air out before the pressing stroke takes place. Okay, well, I tried to convince you that a lot of things can happen prior to forming the shape. But now we're going through a drying process as we may find necessary. And we're going to make a 90% alumina refractory. Okay, now I'm going to talk a little bit about older technology. Okay, and in the refractory products, when you look at the microstructure, you can make that two ways. You can make the product with fused alumina aggregate with a lot of matrix containing mullite around it. This matrix and product was formed using some tab and calcined alumina along with silica sources, but the main thing is the fused alumina in the matrix. A second way to beat about the same chemistry specification is to use tabular alumina. Here's a grain of tabular alumina. You can see the little crystals developed, and what's harder to see at this magnification is direct bonding, but occasionally you'll see direct bonds between mediums and the matrix phase into the fused alumina aggregate. So to make the strongest possible product, we want to have these bonds extending across the matrix between the coarse particles. So we expect glass to form. The minimum eutectic can be pretty high, 1600 or about 1600 degrees Celsius. If we use some active fluxes, some lithium aluminum fluoride phases, for example, eutectic can get down to about 875 degrees C or thereabouts. So we can form glass at a little bit lower temperature than the normal, as in porcelains. That again is the advantage of the intensive mixer. We can use a very small amount of a very active flux, and we can disperse it readily throughout this matrix and be successful with what we do. So I won't go over all these properties, but anyway, here is a slide with some of the properties of these products, and really it's interesting to compare the fused alumina mullite matrix and the tab alumina matrix, which also contains corundum and mullite. And both of them are up right around 90% alumina. You begin to see some differences when you get here into the area of apparent porosity. Specifically, you'll see a lot of differences in modulus of rupture. So the lower the silica content with a higher alumina matrix, we're going to more direct bonding. We're going to have higher modulus of rupture. Of course, that's especially true at elevated temperature. We can have very high crushing strengths with these particular products, and permanent linear change, PLC, that's the shrinkage on reheating, in this case to 1705 degrees Celsius. We get very little or no shrinkage, particularly in the one with tab alumina. Another difference is in this so-called panel spalling loss. The panel spalling test is a refractory test where a panel of bricks is preheated, and then the panel is opened up with an air blast in it. There's a certain number of cycles for that, and the percent of material that spalled off or cracked off and fell off during that test is a lot different. Now, of course, there's the alumina chrome products. Here spoke of these in an earlier lecture, some of the chemistries of those. Essentially, the spall resistant product has a much higher percentage of small pores in it than does the traditional product. Okay, so we have a dual bands of pores in both products, coarse pores and fine pores, but a lot more fine pores in the spall resistant product. The way this was explained to me by a professor a long time ago was when they first came out with automobiles, a Model T Ford. If you had a crack in the fender and couldn't do anything else to fix it, you couldn't weld it, then you could bore a hole right at the tip of the crack, and that would blunt the crack tip and stop the progression of the cracking. And that's kind of the idea in improving the fracture toughness of alumina by increasing the fine pore fractions. Okay. Well, just to reinforce what I just said, a unimodal pore size distribution is one like shown right here. In other words, most of the pores are right around a particular size, and this is showing it just above about 10 microns or thereabouts. But if we fire to a little lesser extent, this may be maturity and this may be a little bit immature, then not only do we have those pore sizes up here above about 10 microns, but we start developing pores down here below 1 micron, between 1 micron and 1/10 of a micron. And those are the fine pore sizes that provide the spalling resistant. So you have to define maturity in terms of what characteristics you want in the product. And pore size distribution then becomes just as important as porosity and strength. So what we talked about in these alumina porcelains are 90 to 95% alumina compositions is that you want to allow time for liquid phases to develop, which might say you want to ramp in the firing schedule. You want to allow the liquid phases to develop, and once you've given them time to develop, you can ramp up to higher temperatures to enhance the sintering process. Remember that primary mullite is the main thing that you're looking for, because the liquid phase percentage is so small, secondary mullite really doesn't come into play. So that's for reactive sintering. Firing strategy number 3, don't overfire the product if you want to maintain fine porosity for the reasons that I said. So here's an example number 2 of a 99% alumina refractory product. This example is taken from a technical paper on the Almatis website. I want to give the authors full credit for everything that's been given here. And so let's go through what they've done. Now, when we're up at 99% alumina, we're going to not have a liquid phase that plays a substantial part in bonding. Okay, we may have some fluxes distributed along within the matrix among the aggregate particles, but with 99% alumina, what we're going to do is cause direct sintering, solid state sintering between the particles. You should have taken more courses on this than I will spend time upon here, but solid state sintering is usually a thermally activated process. You have to get up to the temperatures required to form those sinter necks. So temperature and time and reaching a high temperature are very important. Of course, in solid state sintering, we get bulk diffusion from the interior of the particles, in this case, corundum grains and corundum particles to points of contact. And we get surface diffusion to those points of contact. The object is trying to minimize its surface energy by forming these sinter necks between the particles. course, any diffusion control reaction means we have to get up to sufficient temperatures to cause atom movement to take place. And usually that's a fairly substantial percentage of the melting point temperature. Now, the raw materials used by these guys were tab alumina, and they also were comparing some mixes to Chinese white fused alumina grades. They were trying to look at compositions that had the best slag corrosion resistance. These compositions contain CT800FG. Here's some information on CT800FG. You've seen it earlier, but we only have a very small percentage, plus 325 mesh, 0.1%. The median particle size is 3.5 microns. The specific surface area is 0.9. When you look at this tabular alumina aggregate, back to the tab alumina, you can see little black pores here scattered among the microstructure. So we're going to look at some of their mixes. Now I've given you all their mixes. So what they did was look at tabular alumina, 100% tabular alumina. All the tab fractions are given in red. Coarses, fine coarses, mediums, and fines. They used some calcined alumina along with the ground tabular alumina. Why? They wanted more reactivity here. For sintering, they used sulfate pulp liquor. In the United States, that's called gulak and glutrin. Very commonly used in ceramic plants. It has kind of a burnt sulfur smell, burnt toast smell to it. Used to be able to walk around outside a plant and tell that they were using glutrin and gulak as the binder in dry pressing. So this mix had 100% tab. Now they made some other mixes at lower percent tab alumina, and then they made one with only a very small or negligible amount of tab alumina, a little bit of calcined alumina here. I think they used white fused alumina fines here. And so, again, they were using the CT800FG to encourage sintering. Now, a comment on processing. So they were mixed well with binder and a high-speed mixer. Well, I hope so. And they used a friction press or impact press with a maximum impact force of 6,300 kilonewtons. I had to convert that into pounds per square inch, and that would say a maximum was about 35,000 due to the impact. That doesn't mean that the press reached that pressure, but typically in these presses, you'll give a light impact to de-air, have a little bit of dwell, and impact one or more times to get toward the final density. And then they said they fired at 1750 for 8 hours. So it's a little bit unclear exactly what they did, but 8 hours was probably the total firing time, meaning from room temperature up to 1750, which would take a few hours, maybe 3 or 4, and then the balance of time at the soak temperature, and probably the kill was allowed to cool naturally at that point in time. So that was their processing situation. Now we're going to look at some of their data. And there's a lot of data here. You can look at the apparent porosity. They say the 100% tab alumina composition was about 16% porosity. The bulk density was up here about 3.26. Well, the true density of aluminum is about 3.95, although the tab wasn't quite that dense. So you can see that there, if you do a little bit of Sherlock Holmes investigation, there probably were some closed pores as well as open pores. So this apparent porosity represents the open pores. And of course, they got just under 1.4% shrinkage in firing. The fused alumina is, of course, much larger crystal size. It's going to be less reactive than the tab alumina even. And so less firing shrinkage is probably expected. The authors report the highest cold crushing strengths for the tab alumina mixes in excess of 140 megapascals. And if you multiply 140 by 145, you'll get that in pounds per square inch. Interestingly, they compared the cold modulus of rupture to the hot modulus of rupture. And the hot modulus of rupture was, of course, less, and that's very typical for these kinds of materials. But again, they found the tab alumina compositions to be superior. And there has to be a reason for that. And so they showed a microstructure of a white fused alumina brick. And look at these areas that I've circled in red here. There's some cracks around the fused alumina are the big particles, the coarse particles, and there's the voids. They didn't fill this space very well in their high-speed mixing process, whatever they did. Now, in all fairness, people who work with microscopes know that you can pull aggregate out during polishing. So I can't 100% tell you that this wasn't pull out, but my guess is they just didn't do the best job in the world of filling this microstructure around these fused alumina particles. It's not easy to do, and there are a lot of cracks in this microstructure. In one case, the fused alumina articles were superior, and that was in abrasion resistance. And of course, fused alumina is a very, very high hardness material, and maybe you would expect that. Well, that concludes what I have to say about 99% aluminum refractories. Where can you find information on other processing steps? I always teach students to look in patents. So wherever you are, you can look at patents. In the United States, you can simply Google uspto.gov. That's US Patent and Trademark Office.gov, uspto.gov. And you can do your own search from your own computer. So I just searched the keyword alumina and the keyword Kyocera under assignee. And this is one that popped up, alumina centered article. Okay, and so that's from 2012. And it is a source of information. Now, patents are written by patent attorneys, and patent attorneys don't want to give away all the trade secrets of an organization. So, for example, they say here the compositions which they were trying to make low dielectric loss ceramics, but for electrical application, they were fired between 1500 and 1800 degrees Celsius. Or you're not going to fire at 1800 degrees Celsius for something like this, I don't think. So as you can see from our previous example, firing up to about 1750 was about the maximum that you could get. So you can be aware that in patents, you're going to get attorney speak, attorney's language, but you can get a lot more information. And I have a lot of respect for the company Kyocera, and I know why the patent attorneys did this, and they did the right thing. But you can look at patents anytime you want to get further information. In patents, I usually look at the examples because it tells you how they do things. It doesn't tell you every secret they have, but it'll tell you a lot of information on how they do it. So firing strategy number 4 is to reach a maximum temperature, to reach the density and strength goal that you have in the soak period. Do that for the amount of time required to complete the centering If you've done everything right and doing the right particle size distribution, doing the mixing right, using the binders right, burning the binders out correctly, using some reactive, more reactive aluminas in the composition, then in fact, you're going to make the property goals that you have. So we looked at two examples, 90 to 97% alumina, those that contain a fair amount of silica that are reactive. Sintering takes place, forming mullite, a new mineral in the matrix. The glass may go away some or almost all. It may disappear in the sintering process. Then we looked at 99% alumina. And there we had a chance or an example where people played with the reactivity of the aluminum oxide to enable them to make the products at particular product standard goals. Well, I hope that was interesting to you in firing alumina. It's certainly not comprehensive because you could have a whole course on firing alumina. But it's a little bit different firing situation. It's the first case where we've had direct bonding of the majority crystal in phase, corundum, aluminum oxide crystals, direct bonding across the matrix to give the physical properties that we wanted. And liquid phase played a minor part or no part in achievement of the fired microstructure, the fired properties. Now, the next class will be about firing cordierite. And I chose cordierite because I've worked with it a lot. And you have to meet a composition goal to make cordierite. It's a very specific composition goal. And there are ways to figure out that you got there, simple and complicated ways to figure out that you got there and making the cordierite. And it's going to be the last lecture in the first unit about firing materials, considering their composition and the internal structure of the products. After cordierite, we'll go into unit 2, which will be about kilns and furnaces and combustion. And if that's what you've been waiting for, then good for you. So I hope you've enjoyed today's lecture, and we will talk in the next class about my favorite subject, cordierite.